Okay. All right. Welcome back, everyone. So this is the last lecture of the fall quarter 564 class. And then how many of you are taking 565 next quarter? Are any of you not taking 565 next quarter? Okay. So I'll see most of you in the next quarter, which is great. Let's see. A couple of things. Okay, you're going to get an email for online course evaluations next week. So please fill those out. Give some indication of what worked in the class, what didn't, if you learned something or not. So these are really useful for me and also for the department to tell whether or not I should be teaching here or not. Okay, about the exam. The exam is due today at 5. I've already received exams from about 10 of you, so that's great. I wanted to point out one little thing. So in the course notes, so how many of you have started the exam? Have any of you not started yet? It's okay. Okay, good. So I'm going to talk about it a little bit because all of you have probably seen it. Sorry, I didn't want to open the exam. I want to open the lecture notes. So there was a lecture where I talked about finite difference derivatives. I think it was this one. And essentially I derived kind of the error, the minimum error for like a delta x for a finite difference derivative scheme. So some of you probably have seen this. The first part of this is all fine, but I made some major mistakes when I was doing the actual evaluation of the delta x. So I just want you all to be aware that if you're following my notes, you should actually really do this problem again yourself, because there might be some minor errors in the details of my derivation, but the idea is basically there. So I just wanted to tell you because I feel like it would be kind of unfair to have a wrong solution to an exam problem in my notes and not tell you about it. Can anyone guess what this plot is of? Any ideas? Okay, yeah, so what does PCA stand for? I heard you say it. I think you know. Anyone else? Okay, what does PCA stand for? Principal component analysis. So here, this is actually kind of an amazing data set, really phenomenal. This is the amount of money brought in by each of the largest 13,000 insurance carriers in the US, along features defined by what kind of policies they issue. So this is the kind of... This is just a teaser for some of the kinds of things we'll do next quarter. Next quarter, we're going to focus on partial differential equations, but I'm also going to tell you a lot about data analysis. So how do you essentially take very, very high-dimensional data? I think this insurance data, we had 64 gigabytes of policy information over 200 million insurance policies over 20 years. But you can distill it down to these very simple, actionable, interpretable results where if you're over here on the left with these red large circles, that's good. You're making boatloads of money. And if you're over here, you're not making hardly any money at all. Okay, so this is like a very, very simple distillation. So I want to teach you about data skills, and I want to train you all to be essentially data consultants, because that's what you're going to be for your advisors in a number of key points in your career. Okay? Let's see. So today we're going to revisit this double gyre example. Okay? So this double gyre is an example that we derived at the very end of class last time. So we have this stream function. Psi of x and y is given by sine pi x, sine pi y. So it's periodic in x and y. And you can define this vector field V by taking the partial derivative of the stream function with respect to y and x, just like we did for potential flow. So stream functions and potential functions are pretty similar in how you use them. And so we derive this vector field V given by pi times sine pi x cos pi y, and the y component is minus pi cos pi x sine pi y. Okay, so the first thing we're going to do is plot this in p-plane and get a feeling for what this vector field actually looks like. And then I'm going to add in a time-varying spatial frequency for the x component. So I'm going to have this system start to move in time. And we're going to do all kinds of interesting analyses. We're going to look at where particles go. We're going to look at where this flow is sensitive to initial conditions. So if you were going to drop oil, there are some places that would be much better to drop it than others. Okay? Or if you want to track an oil spill or a contaminant release in this kind of a vector field, we're going to start to get to some of those ideas today. Any questions about this double gyre before we kind of jump into some Matlab code? Yeah.
Does the 1, 1 point on there end up acting like a saddle point then because of the boundary?
The 1, 1 point definitely looks like a saddle point, exactly. So if you looked at what was happening above this, I think it would look like a saddle point. So there's a fixed point right here where if you're exactly at that point, I believe that your velocity field is 0. Yeah, so all of the corners are every integer location on the integer grid is a fixed point of this vector field. And some of them are saddles. In fact, I think all of them are saddles. Yeah. Yeah.
What's the center like? 1/2, 1/2.
So 1/2, 1/2 might, what is that? Yeah, so that would also be a fixed point, right? So sine of pi halves, sorry, cos of pi halves would be 0, yeah. And that's the center. So that's a good point. So what you could do here, if you wanted to, maybe someday this will be on one of my exams, is find all of the fixed points for this double gyre system and then characterize them into saddles and centers. Okay, so let's actually code this up. So I've already started. I have p-plane open. And let's see if I can do this. Okay, so in p-plane, I have this vector field defined over all of x and y. The x component is pi sine pi x cos pi y, and the y component is minus pi cos pi x sine pi y. And we're deriving, we're going to show this on the interval from 0 to 2 and 0 to 1 in the y direction. And I really hope it looks like what I think it should, and it does. Okay. So if I click on this, you can see that the closed curves really are circles. This has some numerical inaccuracy, so it's losing energy, but that's just because it's numerically not integrating it very well. Okay, and so that's the basic idea of this vector field. Okay, so I have a vector field defined on all of space. And I've kind of zoomed into the spatial region from 0 to 2, 0 to 1. And now what I can do is I can use that vector field as the right-hand side for a set of ordinary differential equations. Okay, so let me write this down. I have this vector field which has two components, v1 and v2. And v1 and v2 are both functions of all of space, x and y. And so I could say that x dot equals v1 of xy, and y dot equals v2 of xy. Okay? And this is where you would find the fixed points are saddles and centers, and you would look at the stability and do all of the stuff that we did in the first half of the class. So does this make sense how we can take a vector field and we can then integrate particles through that vector field? Okay? We could do it analytically. If this was a simple system, we might be able to actually, if this was a simple V vector field, then we might be able to find a solution by hand. But what we're probably going to have to do is use something like ODE 45 to get a numerical solution to this vector field. And that's exactly what p-plane is doing. You define a vector field, and then it essentially integrates particles using ODE 45 to see what their trajectory would look like. Okay? All right, good. So now what we're going to do is we're going to change this vector field a little bit. So how am I going to do this? Okay, let's make sure I can actually do this. Okay, so I'm going to change my vector field a little bit to make it time varying. And this is going to be pretty, like a pretty simple change, but it's going to actually make a huge difference. So before, my stream function was psi of x and y equals, what was it, sine pi x, sine pi y? Yeah? Sorry? Sine pi x, sine pi y, and then when I took the partials, I got sine, cos, cosine. So what I'm going to do now is I'm going to make this all I'm going to change is I'm going to add a frequency a time varying frequency. So my new psi is going to be sine of pi f of t x sine pi y. Okay. And this f is actually, let me see. This is actually going to be a function of both x and t. Okay, my frequency is going to depend on x and t. And so and let's think about what this means. So if I have a time varying frequency x, then that means that the spatial oscillation frequency might be speeding up or it might be slowing down. Right? And having this f as a function of x means that essentially what I can get is instead of equal and opposite vortices, what I'm going to have instead are unequal and opposite vortices. So I'm going to have one larger one that's moving faster and maybe one smaller one that's moving slower. So that's what this f of x and t is going to allow me to do, is have the system kind of oscillate back and forth between having one really big vortex on the right and then one really big vortex on the left, and they're going to go back and forth. So this f of x and t is given by ax squared plus bx, where a is a function of t. So a of t is some epsilon times sine omega t. Okay, you can kind of work through why this does the things we want it to do later. The basic idea is that this frequency has a couple of zeros, and those zeros change as a and b change. B is 1 minus 2a. Okay, I didn't come up with this. Some like ocean engineers came up with this function that does what they want it to do. But you can still do the same thing. You can say that v1 and v2 equals, and I think it's partial psi partial y and minus partial psi partial x. And when you take partial with respect to this x, now you not only have a cos pi f of x times x, but you also have an f prime of x. Okay? That's basically all there is. So I'm cooking up this new stream function, and this stream function has an x frequency, a spatial frequency, that varies both in space and in time. Okay? So I'm going to code this up, and we're going to see what this does to our double gyre vector field. Okay? Any questions about that stream function before I move on? I mean, I didn't tell you much about it. I kind of just made it up or wrote it down. Okay. So I suppose we could have actually plotted this in p-plane. We could have picked a value of a and b, and we could have plotted the instantaneous vector field in p-plane. But I think what I'm going to do instead is to actually just solve the whole problem. So here I'm defining a right-hand side vector field. Remember in ODE 45, to integrate particles, you need a right-hand side. So I need to define these functions v1 and v2. Okay? And so this double gyre vector field is time varying, so it's a function of time. It's a function of the spatial location, which I'm calling y. This is a vector of the x and y positions. And it's a function of these parameters a, epsilon, and omega, which I'm going to lock into place, because these have been kind of defined already by the geoscientists. Like, they know what a, epsilon, and omega should be for ocean systems. Okay, now remember when we did the Lorentz equation? We did a big for loop for, for I equals 1 to whatever, for j equals 1 to whatever, for k equals 1 to whatever, and it sucked. It was super slow. So instead, we decided to have a vector-valued state where this y(in) is actually a huge array of the x initial condition over all of the grid points I define. And the second component is another huge two-dimensional array of the y initial conditions over all of the initial conditions I'm defining. Okay, so this y(in) is really a three-dimensional array. It's got a v1 and a v2 component defined for an entire 2D array of grid points. So on my entire spatial domain, let's say I have 100 by 50 points, so I have 5,000 grid points defined. Okay, then this is going to be size 2 by 100 by 50. Okay, and it's going to be the x and y positions for all of these 5,000 points. Okay, so this, for example, if I define this huge grid of particles, this y(in) is going to keep track of the x and y positions of all of them. Okay, so now I'm defining my actual velocity field u and v. Here I called it v1 and v2, but here you can call it u and v. It doesn't matter, as a bunch of zeros. And then I'm going to populate them with values based on my stream function. Okay, so I have this a value, which is epsilon sine omega t, b equals 1 minus 2a. I can define f and the derivative of f with respect to x. This is my time varying, spatially varying frequency. And then I can define my u and v velocity components by taking the partial derivative of my stream function. Okay, so this is exactly what we did for the simple double gyre that was stationary, but now we've done it for a time varying frequency f in the x component. So you can kind of work out, I should probably give you a reference to the paper where this vector field is defined, but it's pretty straightforward from the stream function that I wrote down to get this u and v. You just take partial of psi with respect to y and partial of psi with respect to x, and you get these two components. Okay, I don't want to spend too long on this because the specific vector field I'm choosing doesn't really matter that much. Some smart scientists decided that this vector field modeled a physical system they care about. Okay, there's an ocean model, and there's this vector field that models the ocean in a particular way. And what this code does is it returns the u and v velocity components for every single particle in my grid defined by y(in). Okay, so I had this huge grid of particles defined by y(in), and the output is a huge grid of u and v velocities for each of those particles. Okay, and then I stack it into a three-dimensional array. Okay, let me just double check and see if anyone wants to talk about this before we move on to actually integrating the vector field. Does the basic idea make sense? We have a vector field, we're looking at particles in the vector field, and I can define the velocity at each of those particle locations by taking the stream function derivatives. Okay. Okay, so this is where it gets fun. So here I'm going to make a function called integrate double gyre temp. So we're going to integrate this thing now. Okay, so first what we're going to do is I'm going to essentially define a big grid of initial particles. And I'm going to ask what is the velocity at each of those particles, and I'm going to plot it. Okay, makes sense. So let's say A equals 0.1, eps equals 0.25, and omega equals 2 pi over 10. These are the values from the model. Okay, these are the values that somebody defined as good values for the model. And so part 1, we're going to initialize a grid of particles and integrate through the vector field. Good. Okay, so for this grid of particles, I get to decide what is my delta x and delta y. Like how many particles do I have? What is the resolution that I'm going to start looking at this system? And in real life, I would use something pretty small like 0.01 or 0.001. But to make this fast and kind of reasonable, I'm going to choose kind of a coarse dx just so we can see things move quickly. So 0.025, this is a coarse delta x. And now I'm going to define a vector of x coordinates and a vector of y coordinates. And then we're going to use those to create this mesh grid array of initial conditions, just like we did for the Lorentz system. Okay, so my x vec is 0 in increments of dx to 2. And my y vec is 0 in increments of dx to 1. And if you wanted a separate dy, you could have a separate dy. But I just want it to be uniform spacing. And then I'm going to say x naught, y naught equals mesh grid of x vec and y vec. This is my grid of particles. And at this point, I probably should be able to actually plot them. So I could plot x naught and y naught, and let's plot them as red dots, kind of large red dots. Hopefully this works. Good. That's my grid of particles. Okay? All of those red dots are my grid of particles over this domain. Okay? So how many of you remember this mesh grid command? Anyone like me to talk about it a little bit more? No. Okay. Right. So I just tell them, what is the range of x's, all the x values, what's the range of y's, all the y values, and then mesh grid populates that 2D array from all combinations of those x's and y's. So what do you think the sizes of x naught and y naught should be? Length of x times the length of y. Right. So let's try that. So if we say length x vec is 81, which is, I think, 2 divided by 0.025 plus 1. Okay, length of y vec should be 41. And then size of x naught is 41 by 81. Which is a little bit weird. So this is actually not what I thought it would be. I thought this would be 81 by 41. Right? Because my x is bigger than my y, so I thought it would be 81 by 41. But in Matlab, it's 41 by 81. That's weird. So I just take the transpose. Okay? Okay, good. And now, remember I had that variable y in my vector field? Here I'm just going to call it yic. All of my initial conditions, the first component of initial conditions is just x naught prime. The second component of my initial conditions is y naught prime. Okay, so now this initial condition array has 3 components. It has the x component and the y component for the whole 2D array of particles. Okay? So the size of this, if I said size of yic, it would be size 2 by 81 by 41. Right? I've got an x and a y component for each of those grid points. Okay, good. All right, so now we're going to plot everything. Plot everything. So here I'm just going to move this down. Okay, so I want to do something kind of cool. I want to say subplot 2 by 1 by 1. And what I want to do is I want to have 2 plots. I want to have a top plot and a bottom plot. In the top plot, I want to actually visualize what my vector field is doing, like in p-plane. And on the bottom plot, I want to visualize what my particles are doing as they integrate through. Okay, so in my first subplot, I'm going to define dy equals my double gyre vec of at time 0 with y initial condition, a eps omega. And there's this super cool command called quiver. Have you heard of quiver? Yeah, so quiver is awesome. If you give it a bunch of u and v velocities on a grid, it will essentially plot them like in p-plane. Quiver, because you have a quiver of arrows, right? It's a bunch of arrows. Okay, so we're going to use the quiver command, and we're going to plot yic, the x component. Let's see, this is going to be super long. So I'm going to plot okay, so quiver takes in the x component of yic, the x component of the position. Then it takes in the y component of the position. Then it takes in the x component of the vector field. Then it takes in the y component of the vector field. Sorry? Yeah, so I called this y component. So I dumped out the vector field into this dy object. Okay, so quiver takes in x component of the position, y component of the position, x component of the velocity, y component of the velocity, and it draws those velocity arrows at each of those positions. Okay? But if I run this, I think it's going to be a little bit weird. Let's see. I have to change folder. Okay, so it's a little hard to see that because there's so many values that I'm plotting. Right? There's so many of these arrows. So what I'm going to do is I'm only going to plot every fourth value. I'm going to say 1, 4, end, 1, 4, end. I'm only going to plot every fourth arrow. And now it looks a lot better. Okay? And I should probably also do some nice plotting things. I'll say axis 0 to 2, 0 to 1. And I'll say draw now. Okay, cool. We have a vector field. It looks awesome, right? And this for time 0, this is exactly the double gyre vector field. But as we increase time, this thing is going to start moving left and right. Okay? Good. And now in subplot 2 by 1 by 2, we're going to do our plots of all of our red particles. And I'm going to do the same thing with axis and draw now. Okay, good. So now this is actually pretty simple, right? It took about 10 lines, and now we have this great graphical template. And as we integrate this set of particles through this vector field for each dt, we're going to be able to see how the particles move and what the local velocity field looks like. Okay? Questions about the plotting techniques or anything at this point? Just interrupt if you have questions, please. Yeah.
Change any signs in the stream function from what we plotted in the p-plane?
Mm-hmm. Yeah, I have a minus sign in the v component, but it doesn't matter. It's now the flow is going down instead of going up, but it's the same. I couldn't find a good convention for what the sign is on the stream function, and I haven't derived it myself in a long time, so I'm just using what's in the paper. Okay, good. So that was part 1. Part 1 was initialize a grid of particles. We didn't integrate through any vector field, so we just initialized a grid of particles and we plotted them, right? So part 2, now we're going to integrate these particles through the vector field. Okay? Part 2, compute trajectories, i.e. integrate. Okay, good. So now we've already defined a dx and a dy, and we have our grid. But now we need to define a dt. Bless you. So for dt, we're going to say 0.025 again. This is my time step for integration. And I'm going to integrate from time 0 to time big T equals 15. This is the duration of integration. So we're going to integrate from time 0 to 15 in increments of 0.025. And at every step, we're going to keep track of what all of those red points are doing and what the vector field that they're living in looks like. Okay, good. So first part is to actually integrate this thing. Let's see. So y in equals y initial condition for I equals 1 to t divided by dt. And what do I do? Time equals I times dt. So first thing, I'm going to plot my new vector field because my vector field is changing. So my top plot is going to be changing at each of these dt's. So I'm going to go back to subplot 2 by 1 by 1. And I'm basically going to do this thing again. Okay. Except I'm not going to be running my double gyre vector field at time 0 and y initial condition anymore. I'm going to be running it at time t and y initial condition. Okay, right? This time is changing now. So here I'm going to say that I'm running this at time equal to time. Okay, seems pretty reasonable. And the next thing I'm going to do is I actually need to integrate my particles. So this was just plot vector field. Now we're going to integrate particles. And to integrate the particles, I'm going to use my RK4 single-step Runge-Kutta integrator that we derived for the Lorentz system. So here I'm going to just use RK4 single-step on this double gyre vector field. Okay, so what did my RK4 single-step take in as inputs? What do you need for a Runge-Kutta integrator? What does ODE 45 take in as inputs? A right-hand side function and initial conditions and a time step probably. Yeah. Okay, so what do we have? Okay, so y out equals RK4 single step. And I have to give it a function of t and y, which is my double gyre vec at t and y with the parameters a, eps, and omega locked into place. Right? A, eps, and omega are those three parameters that someone else defined. And I'm just locking them into place to force this to be a function of just t and y. And then I also give it my dt, my current time, and my initial conditions yn. So you can look up, these are the four arguments that I need for RK4 single step. I need a right-hand side vector of just t and y. I need a dt, my current time, and my set of initial conditions I'm going to integrate. So I take y in, and I get y out. Okay, that's one time step. And at the end of that time step, I'm going to say that my new y in is y out for the next time step. Right, at the end of every time step, this y out becomes the y in for the next integration. Okay, so the last part is to plot the particles. And I'm just going to copy and paste this part here. Draw now, yeah, so usually if you ran this without draw now, since it's computing so many frames, it would wait until the computation is done and then show you the last one. But with draw now, it's going to update every dt.
And then why do we need it for the initial, not for the initial condition without?
You probably don't. Well, it might be that if I just ran the whole script, it wouldn't show you that one. It would just start showing you these. Yeah, Matlab's weird. I just put draw nows when I can't see things that I want to see. Okay, so now what we're plotting are the particle positions of y out. What do I want? Y out 1 colon and y out 2 colon. Now this is super weird. What's the how big is this y out and y in object? What's the size of these things? How many dimensions do they have as arrays? How many of you think they're one-dimensional arrays? Two-dimensional arrays? Three-dimensional arrays? Okay, so the 3s have it. This is a 3-dimensional array, right? It's got the x and the y position of all of my 2-dimensional grids. So this would be size 2 by 81 by 41. So this is a super bad notation that I'm using, but this is apparently good Matlab code, is if you have a multi-dimensional array and you say, anytime you say colon, it essentially takes every other dimension of the array and it just stacks as a really tall column vector. So I'm taking the x and y position, I'm taking the x positions and I'm turning them into a huge column vector with this notation. And I'm taking the y positions and I'm turning them into a huge column vector with this notation. Super confusing until you get the hang of it. Like, you should try this out sometime. Like, for example, if I say vec equals 1s 2 by 3. Okay, so I have this big, maybe I should call it mat equals 1s 2 by 3. So size of mat is 2 by 3. But if I say mat of colon, I get a huge vector of 6 1s. Weird, okay? But it's Matlab. So weird's okay. And I think that's it. I'm going to run this. Let's see if something interesting happens. Okay, so we have an integrator. And for every dt of this integrator, we plot the vector field. And notice that I'm plotting the vector field using my initial conditions, because I'm using that regular grid I started with. I'm not using my new points, because I want to know what the vector field looks like on the whole regular domain. Then I take a time step. I advance my points 1 dt in the future. And then I plot the points. I really hope this runs. Yes. OK. Good. And what we're seeing is, every dt, all of the particles being advected by this time-varying vector field. The cool thing is that this is a real research problem. It's a toy problem, but it's a sophisticated enough problem with chaos and high dimensionality and relevance to physical systems. Actually, I have 3 papers I've already written using this double gyre vector field and this toy code that you're about to get. So you can do really, really cool things with this and actually kind of make advances in theory using this simple model. Does anyone want me to run this one more time? Yeah, one more time. Let's do it again. OK, so the blue field is oscillating. The left vortex is getting bigger. Now the right vortex is getting bigger. And as that happens, you see that these particles are getting kind of mixed up into these basins. And one hypothesis that you might have is that from the particle's point of view, this is a chaotic vector field. Meaning, if I took 2 nearby particles and I ran them through this thing, they might end up kind of exponentially separated in a short amount of time. That's what chaos means. That's absolutely true, and that's something that we actually get to explore with this. OK, are there questions about what we've done so far before we do the chaos part? Yeah?
Just on the code, what regulates how fast it's drawing?
How fast my computer can do this integration. So my computer is just hauling ass right now trying to integrate all of these particles. And every time it gets an answer, it plots it. Then it tries to integrate another set of particles. Once it gets an answer, it plots it. So this is limited by how fast my computer is. Yeah, if I want it to pause, I would say pause 0.1. Now it's going to pause for 0.1 seconds every time. You can see it doing that, right? It's like tick, 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 tick. So it's got a built-in DT pause. But I don't like that. I want it to go as fast as possible. If I had a smaller dx, like if I actually used a reasonable dx, like what I might do in a research problem, oh, that's not a reasonable dx, then it's going to be a lot slower. Not too much slower, actually. It's doing a pretty good job. In fact, I'm going to keep it. I like this. Because you can really start to see these very interesting patterns that are developing in the flow. So for example, let's say that, what's a good example? Let's say that this is Oregon and this is California. These are the coasts, okay? And I live in California and I'm going to dump pollution So what I would do is I would drive 2 miles north to Oregon, and I would dump my pollution right here because it's going to get carried out into this Oregon gyre. Okay, and I'm not going to dump my pollution on the California side. And it turns out that this actually is a pretty valid model. Like in Monterey Bay, there is a gyre, and there is a line you can draw in the sand where if you dump pollution on one side, it gets carried out to the deep ocean, and you don't have to worry about it in the short term. And if you dump it on the left, you're in big trouble. Okay? So the next part of the analysis I'm going to show you really starts getting into this idea about where you would start dumping your pollution. Let's see if I can do this. I am going to jump to a code that is completely written. Okay, so magically we have about 50 or 100 new lines of code here. And let's see if I can just bring this in.
What does graphics on do?
Graphics on is a flag that I define. So if I turn it to 1, then it plots things. If I don't, then it... So the plotting actually slows my computer down a lot. It's like 10 times faster if I don't plot stuff. So sometimes if I want results, I just turn all the graphics off. And tick and talk is to time the code to see how fast it runs. So I'm just going to quickly cut and paste some code into my code, and it's going to break everything. Let's say I define graphics on equals 1. Okay, so now I'm doing something funny. So I'm taking... shit, I shouldn't have done this. Okay, I'm going to go back to my working code. So for every dt, I integrate through this thing, right? And I plotted, and I plotted, and I plotted. And at the end of that dt, what I'm going to do is I'm actually going to store my trajectory. Okay, so x trajectory and y trajectory are these monster vectors that actually have the monster arrays that have the trajectory. Okay, good. If I run it through, it cranks through. We'll just let it go a little bit longer. So what I'm going to do is for every single one of my initial particles, right, I had this nice regular grid of initial particles before I started integrating. And I'm going to take a stencil of particles. So I'm going to look at the particles directly to the left and right and above and below my particle. And I'm going to see where did they all go. And I'm going to essentially use those neighboring particles to approximate the derivative of where particles go with respect to x and y. And I'm going to plot, so that is a weird matrix of derivatives. I get this matrix df, d flow map is, partial f partial x, partial f partial y. This is the first component. Partial f partial x, partial f2 partial y. So the derivative of the x position with respect to x, the derivative of the y position with respect to x position with respect to y, and so on and so forth. And I'm going to take the largest eigenvalue of this, and I'm going to plot it. Because that tells me if I have a really large eigenvalue at some point, that means that my neighbors went way far away from me in some direction. We don't know what direction, but in some direction. Okay, let's look at size of xt, just because I'm curious. I don't remember what I did here. Okay, that's just the x, and that's the last point in my trajectory. So this means x at time big T. Okay, so I'm computing the finite difference derivative gradient. Just like I said, I'm going to compute this finite difference of all of my final positions with respect to my initial positions. Then I'm going to pull out the largest eigenvalue, and I'm going to plot this thing. And what I see here, these are these high color values, the bright yellow regions, are where the flow is the most sensitive to the initial condition. So, for example, right here, if I start a particle right on that yellow ridge, then what this is telling me is that particles to the left and right and above and below are going to very, very different places. And that makes a lot of sense in this double gyre, right? Because I have this separatrix. If I started, left or right of the separatrix, then they're going to very different places. They're on the saddle point, kind of. So this is like the time-varying analog, kind of a saddle point. We have these particles going to very different places in time. And we just got this from looking at the particle trajectories and calculating the derivatives and the maximum eigenvalue. So you can go through the code and kind of figure out what this means and what this is doing. You could also plot it as a surface if you like. Right, so height here indicates that you're getting a lot of separation between neighboring initial conditions. So places where there's a lot of height, you get a lot of separation from neighboring initial conditions. And so finally what I'm going to do is I'm going to define, let me just run this one more time. So now what I'm going to do is I'm going to pick an initial grid of particles in this boring blue region where my math is telling me that I don't get a lot of separation. So these should all stay similar to each other. They should stay close to each other. And I'm going to take another patch that is straddling one of these funky sensitive regions in the flow. And we're going to see that we get very, very different behavior in each case. Okay, so this is, I'm going to run a small patch of particles through, and the particle patch is defined on this region here. So I'm just going to plot this. So that was one patch of particles that I'm running through. They started off in a boring blue region, and notice that they started off together as a rectangle, they moved around, but basically they ended together. Okay, so this blob of oil stayed coherent through this double gyre vector field, right? It stayed in one coherent blob of oil. Let's do another one. So now I'm going to take a patch of particles that was sitting square on the middle of one of those ridges that was very sensitive. And you see that very quickly this thing gets sheared and stretched so that essentially that set of initial particles went to completely different places. There's some all around these boundaries, very, very different places. So this would be like the worst. Well, it depends on what you want. Do you want your oil to stay in a tight ball of oil forever, or do you want it to get spread out to everywhere? So if you want your oil spread out everywhere, this would be the best place to drop it. But if you want it to stay in a coherent blob over Oregon, you want to drop it over here. Okay, so this is, kind of the idea of what you can start doing with vector fields. I didn't tell you how I got that sensitivity map, this sensitivity map here, which I already killed, but the plot where you saw the yellow curves that were sensitive. I didn't tell you why that really makes sense, but it does. I can tell you about that offline sometime. But the idea is with a vector field, I can integrate particle trajectories, and then I can use those particle trajectories to do analysis about where the flow is sensitive to initial conditions. Where do particles go in time? Are there preferred places where oil will attract or run away from? Are there places if you're going to dump pollution, you should or shouldn't dump it? Or if someone's going to, detonate a dirty bomb in Manhattan, we would like to know where the contaminants are going to go in 5 minutes, 10 minutes, 15 minutes. And these are exactly the kinds of analyses you do. You calculate the vector field with some uncertainty, and you would drop a grid of particles, and you would see where they go. And you'd calculate where you should put sensors for chemicals, where you should have evacuation plans, depending on which way the wind is going, and things like that. Okay, I have 1 minute left. That is everything I wanted to tell you. It's been a pleasure teaching you this material in this course, and I'm really looking forward to 565 and seeing you all again. So have a great break, and I'll see you all soon. Thanks.